Okay, finally I succeeded. So my name is Massimiliano Annoni, and I am your professor of advanced manufacturing processes A. I'm sorry not to be here at the first two lectures, but they told me that you have received the information. Um, in terms of organization of the course, you know that everything is already published in the introductory lecture on WeBIP. So everybody can access WeBIP. Okay. So in that lecture, you find also the calendar, the schedule of the course. For sure, my collaborators told you that we made an effort for deciding and putting all of the topics along the semester so that you can know in advance what we are doing in a certain lecture. I cannot guarantee that we won't make any modifications, but we try to follow that schedule. Then, regarding the third things, is there anyone that is still deciding if applying to a certain track or not, or are you all already done in terms of track? So is there someone that is here to check in the first week about the different courses and decide if applying to a track or not? I'm just asking, because if so, I try to convince you. Otherwise, okay, I don't dedicate anything. You were in doubt. You were saying.
I have a question regarding the study plan, but it's not related to this course.
Ah, okay. Yeah, I know. There are many questions about the study plans. You can find the information on the MECEng site. I suggest you to take a look there. Also on the PolyMe site, but especially on MECEng, you have some other information that cannot be found there in the Polytechnical site. Then, since unfortunately I am also responsible for the autonomous study plans, if you have some specific doubts, try to ask me and I will try to answer, which is sometimes these things are really complex. When we modified the master level, our idea was to create many tracks so that once the student decided for a certain track, there were no modifications. In reality, everybody is asking for different things, but in all of the cases, we find the solution. So I'm confident about that because we have done this for some years. So I will ask also to my colleagues if there is something that I should stress about the rules of the course, but I invite you to do the same. If it is something that is not clear about the organization, ask me. In some days, we will prepare the lab work. Every year we have a lab work that is mandatory, and you will be divided in groups, or better, you will group yourself by applying, by filling a certain form. We will upload all of the information soon, also because in theory, if you look at the schedule, and also in practice, we have to respect that. There will be the first lecture about the lab work next week. So we will prepare the preliminary information. It is an introductory lecture. It will be held in the class. And I say this because the object of the lab work is to go to the lab, even if you are not, you are a certain number, but this is manageable. In any case, the first lecture is introductory. So this will happen next week on Thursday. Okay, so instead, now we can start with the overview of the topics. This lecture has been thought for giving you a general information about the contents of this course in advance. Then we will have time to enter into the details of all of the processes, but at least since the beginning, you know what we will say in this course and what you will study. Before coming there, just an introduction about some general concepts. I don't want to make this story too long, but I would like to touch the most important things. You have heard for sure about the industrial revolutions. You know that at the beginning, obviously, human beings used hydropower and fossil power from carbon in order to create energy. This happened in the first industrial revolution. Then with the second industrial revolution that happened at the beginning of the 20th century, 1900, at that time, the concept of mass production came into play, because it was at that time that the Ford company started building the Ford Model T, which is the very first one. Maybe you have seen it. It is the square one. It was made only in black, and it was the example of mass production. The reason why there was just one color was for standardizing the production in order to be able to produce many cars together. But there was no possibility to apply variations. And in fact, we will see in a while that this will be the topic and the objective of the next steps. In the 70s, so here we have about 70 years, another industrial revolution happened. And it is the revolution of the automation, industrial robots and computers. So computers started being used in the industry, both for actuating the machine tools, for example. So CNC started in the 50s, some years before, but in the 70s, there has been the explosion of the automation in the industries. So this could be a little bit misleading, because now that we talk about the fourth industrial revolution, you see many times the robots. And nowadays, the robots are absolutely fundamental in the industry, but in reality, they come from the previous revolution, from the 70s. If you look at the factory producing cars, you can see a situation like this since the last century. So what makes the difference between the third revolution and the fourth revolution? Here you can see already some indications, but what would you say? Because I have in mind just one term. What makes the difference? Let me see if there is already, the solution is already there, but maybe you can find it. And this is something that nowadays is used everywhere, not only in industry. I'm talking about the data. So the difference is that now we want to collect the data from those machines. Machines were already running, so they didn't in reality need such a connection, because you can program a robot and then it works. But if you can collect the data, you can close the loop. You can have more information about how to manage a complex plant. You have sensors, and they are continuously connected. I was saying that there is a relation also with the common life, our common life. We are always connected, but this happens also in industry. And this makes the difference. So obviously we have to work there. And the fourth industrial revolution can be also, if you look at it closely, you can see these topics. So some of these topics are in the frame of this course, because you see advanced manufacturing solutions. Then I will give a brief definition of advanced manufacturing, additive manufacturing. In this course, we make a very short introduction about additive manufacturing. And in particular, my purpose is to underline how additive manufacturing, which seems a new technology, and for many reasons is a new technology, in reality comes from old manufacturing processes. If you think about the laser already existed, and laser is used in the industry since 30 years ago, and now laser cutting is absolutely normal in industry for cutting thin sheets of metal. But in additive manufacturing, it can be used for melting a small portion of material, and then since the laser can go around on a bed of powder, it can melt various portions of this powder in order to create a solid layer, and then you go ahead with another layer. In this way, you can manufacture a 3D part. But the physics at the base of the process is the laser. And I like to underline this point because in this course, we will see, for example, how to design the optical chain of a laser in order to get what we want on the workpiece in terms of power, specific power. So what I'm saying is that based on what you will see about the processes that we study in this course, you can have access also to the understanding of the additive manufacturing, even if I'm not entering into too many details in this course. Then simulation. Simulation comes together with the data, because if you can simulate, especially if you can simulate quickly, you can give an answer in real time to your real system. In fact, now it is some years that we are talking about digital twin. So the digital twin is a simulation of the reality. But in order to complete the concept of digital twin, the two twins must be in contact. Otherwise, they diverge, and so they will be different. But instead, if they communicate, if they exchange data, they can be aligned. So that if something happens in the reality, a certain sensor will tell to the digital twin that there is a variation, and the simulation can maybe understand and react to what happened, and so it can say to the real twin what to do in order to compensate. But this is the logics. Then there are also many others: augmented reality, industrial internet. Industrial internet usually means Internet of Things. So it means that you have to develop a network for connecting the machines of a company, and then you can connect also companies. This seems easy, but this is the major limitation that is preventing the application of Industry 4.0 in the companies. Because it seems easy to plug a cable in the machine and receive data, but in reality there are interfaces. For economical and commercial reasons, many softwares have been invented, so the companies have different software. And you know what happens when you have to pass information from a software to another. At the interface, we have troubles. I can make an example about what happened with Apple. I have Apple, but the purpose is not advertising Apple, but because there are pros and cons. Do you have an idea what are the pros and cons? Even I don't know if you have Apple or not, I don't care, but maybe you have an idea. Let's see if you have an idea. Don't be shy. Someone has Apple? Okay, So you raised your hand, and so now you have to tell something. Why did you select Apple? Yeah, an ecosystem.
Share my file from my iPad to.
Yeah. Yeah, I would add that you can do that easily, safely, quickly, with a percentage of error almost null. But what is the drawback of this?
I can share with Android.
Yes, that's true, and this is a commercial reason. So in reality, we are answering to what I was saying about what is happening in industry. If I have a CNC that is made by Siemens, they don't like to communicate with a FANUC CNC. And the list is extremely long because Siemens tries to sell all of the package, the CNC, actuators, and everything. And they have everything, like Apple, but the cost is high. And if you look at the companies, as I told you, for historical reasons, economical reasons, if you look at the Italian companies, but not only in Italy, they have many different things. Obviously they try to save money, so maybe they buy another software, and so it is really difficult to connect. But only you raised your hand about Apple, so all of the others have Windows or even Google as an operating system. So what is then the advantage of Windows? If there is one. I'm joking. Yeah.
It's super compatible with any other software. So
yes. Yeah, this is a perfect answer because they must be compatible. It is exactly the contrary of Apple. Apple develops the hardware and the software together. They are strictly connected, and in fact, the performance is good. But then they cannot be installed somewhere else. Instead, Microsoft has started exactly from the other side. So they established a standard, but this standard must work on every type of hardware, which is really difficult. So for this reason, maybe Microsoft is not so stable because it is too very complex. I would add also another advantage of Microsoft that comes from the first one. And it is the fact that if you want to adapt, it is in reality exactly the same as the first one. If I want to adapt the system to something new, probably I can. If I'm able, I can go in the setup and I find a solution. Instead, in Apple, this is not possible. You have to stay inside what they have designed, and there are no other solutions. It depends on what you need. But if we think about the industry, we are in the case of, let's say, Microsoft, and we are in the case of many systems that have to talk with each other. And this is really complex. So I want to underline this point because IoT sometimes is under-evaluated. Instead, it is a bottleneck. And the engineers that know how to handle can have a big success in industry. And then there are also other things, cloud for sure, because the idea is that we can share the information not only between machines, among machines, but then we can store in the cloud. You see the advertisement of AWS, Amazon. Amazon is really strong in cloud computing, but not only Amazon, but there are also others. And yeah, I heard that now the richest man in the world is the owner of Oracle. Yes, right, Oracle, which provides this kind of services since long time ago. So the power is in the data. So it is not just an advertisement. It is absolutely true. In industry, consider that exchanging data with the cloud involves some issues. For example, look at this one. The just the next one, cybersecurity. This is absolutely important because when you share data, you never know what happens. You have to build a system that is safe. Otherwise, the risk is that maybe you are doing parts, you are creating machining parts for aerospace, and then this information goes to competitors and so on. So the companies are really jealous, let's say, of their data. Usually they don't want to connect because of these reasons. So there is a need of a big development in cybersecurity. We have a course for the companies. We organize in our department a course for the companies, and there is a nice lecture carried out by a partner of ours, that is RF Celada. They sell machine tools, but two technicians of Celada come in this course, and in a kind of a game, they give instruction to the participants about how to hack the CNC by following some instructions that you can find in the dark web easily. I haven't tried. I say with what they say, but it is really easy to find instructions about how to crack the CNC of a machine. And so since the IT systems of some companies are not robust, maybe it is easy to connect to the Wi-Fi of the company, and once you are there, you can go to the machine and tell the machine to go in the wrong direction, causing a collision, and you create a big damage. I hope that now that I'm telling this, I'm not creating the issue, but I'm just saying this because it is really easy. So we don't have to under-evaluate this. If you want to create a company, a success company, you have to consider all these things. You cannot under-evaluate this. And then obviously big data and analytics. Data are the first reason for building this system. There are many algorithms used for managing data. There are branches, even of engineering. We have a track. Oh, some of you are from that track, right? CM6. I think that I don't think that you are divided in one third. Probably CM6 has more people here, the production engineering. But there are many people of CM6. And so you will study how to handle data. And this is a key factor in the industry. Then usually what I say is that the people that are really strong in managing data, like people from informatics, they need someone else that is more related to the processes. So all of these types of engineers have to work together. It is impossible that only one type of engineer can handle all of this complexity. Okay, now some really introductory concepts. You see that the industry has been really important for the human being in the beginning, with this painting representing some drilling operations carried out by hand in an industry. And now I use these slides just for giving you basic concepts. If we talk about machining, let me see. I just forgot to underline the definition of advanced manufacturing, but it is really simple. The fact is that we would like to use innovative technologies and methodologies for improved competitiveness in manufacturing sectors. Every time you have a definition, take care about the keyword, because innovative or innovative is something that is changing every day. So this is a characteristic of this field. When talking about manufacturing processes, you can really find something new. At every fair, you find new machines, new performances. So if you belong to this field, you must be updated. So you must be aware about what is happening, because there is a risk in manufacturing. The risk is that you have a company, manufacturing company, you do the parts are perfect, or they stay in the tolerance, And so you think that you can go ahead like that for years. But there is a problem, because since the processes are evolving, the machines are evolving, there is somewhere in the world someone that has machines that are more performing. And even if you can do your parts and they are good, there is someone else that is doing the same parts in a lower amount of time and at a lower cost. So for this reason, you must stay updated. You cannot say that it works, my process works, and the parts are in tolerance, and so I'm safe. This is not true. You have to be careful, because maybe a new tool has been invented, and that tool allows you to go twice the velocity, and so this is a boost of productivity. And if your competitor is buying that tool, it is an issue for you. So we have to stay at the edge of the technology. Italian companies are good in doing so. One of the reasons why they are good is that they are small and reactive. When instead you are big, the decisions are not so fast, and I have many examples in mind. So maybe the provider of tools is always the same for years, and so it is more difficult maybe to apply modifications. In any case, if we think about machining, we see that we have a tool that has a relative motion with the part, and this relative motion removes material. So the concept is simple. But under the word machining, we have many processes. Some of them are traditional, sometimes called conventional. Even if I say here that you have to be careful to this definition, because milling, for example, is obviously a conventional machining process, because it exists since I don't know, not a couple, but 1 century. Or yes, something less, but it is an ancient process. But if you look at the performance, and we will see this performance in the course, because we will study high precision machining and precision milling, we see that the development of new tool materials allows us, for example, to machine ceramic materials. You know, ceramics are really hard, but some tools exist and they are coated with diamond. And so you can machine ceramics. That seems crazy, and instead this is feasible. So be careful in judging a process as an old one or a new one. I can make also the example of a foundry. Foundry, obviously, probably is one of the first processes invented by the human beings, foundry. But if you look at what the companies can do nowadays with foundry, you see that there is an advancement. I sometimes post on LinkedIn some videos. I don't know if it is linked here or not, but for example, there is a nice example coming from Ferrari, and they have shown a video about casting of the engine block. You can imagine that the engine block of a Ferrari is really complex, many passages, many oil, and this is made in foundry. It is not made in additive manufacturing. Even if in additive manufacturing they do something for Formula One, because you know, in Formula One reliability is important, but maybe they use some components just for one race, and instead if you sell a car like a Ferrari car, it has to last for a long time, and so there is also an issue like this. But there is evolution everywhere. In any case, if you look at milling, there are many applications, and here the removal of the material comes from a combination of motions. We will make a recap of this, because the mill rotates around its axis, and then there is also a feed motion that gives material to the mill. In fact, feed motion comes from there. we are feeding the meal, we are giving something to eat to the meal. And on the other side, here is an example of laser. Let's see if I can show you. Yes, we will see also others, but this is just an example. From these small video, you can see that there is a certain complexity of the part. So cutting a part like this with another process could be difficult. So in fact, as I will say in a while, the non-conventional manufacturing processes have been invented for a purpose. So they exist because they can solve something different from the other processes. So what I will ask you, and what I think you will gain at the end of this course, is the capability of associating a certain process with the capability, and maybe the possibility to understand how or which are the best candidates in terms of processes for doing a certain part. And here I have put not a versus, but plus, because in the industry, the manufacturing process chains are complex and are made of many processes. You cannot pretend to do everything with just one process. But the good capability of a technologist is the capability of selecting the roadmap, the path, passing through different processes. Not easy, and this is not the purpose of this course, because in this course we see every process by itself. As I told you, I will underline what are the capabilities, but starting from there, you have to play a little bit in order to gain the experience for selecting the processes. Artificial intelligence can help, is starting being applied in this sector, but it is complex. Because if you think about AI, also in this case, I don't want to talk too much about this, but just an example. You know that generative AI sometimes produces some hallucinations. You know, if you use ChatGPT, they are improving. So recently they have less hallucinations. But in industry, we cannot have even one, because if I have an error, maybe I break the machine, I stop the production. So I must be 100% sure that what I have designed is possible. So this is a trivial limitation, even if be open, because there are some evolutions also there. And also in our laboratory, we are applying some AI. For example, there are nowadays some software that help the technologists in using the CAM, the computer-aided manufacturing. They are a kind of plugin that you put in your CAM, and this software is able to decide the manufacturing strategy, the selection of the tools, and the parameters. Probably it works just for simple parts nowadays, but it is evolving. And another example, if I have to make a round part, for sure, I will select turning. Turning is suitable for making axis symmetrical part. I could do something with water jet, but what I want to tell you here is that even if a non-conventional manufacturing process can do something that a traditional process can do, be careful in the evaluation, because it is not just because, I don't know, water jet turning is cool that we select it in industry. Turning is a well-established manufacturing process, is probably the most widespread, even more than milling, and it is absolutely safe, and the performance are wonderful in the micron level range. So what I'm saying is that even if in this course we study advanced manufacturing processes, my message is not you will use only advanced manufacturing processes. You have to use all of the processes and finding the right combination. And another example here. Yeah, I will open that video. But a traditional process is forming. You know, with a sheet of metal, if you have the right press, you can do really complex things. And now I click here, so let's see if it works. This is one of the videos that I repost on LinkedIn. You have studied forming in previous courses, especially if you are from Politecnico di Milano. And so you can see what, differently from maybe what you have seen in manufacturing processes 1, you can see that the complexity can be really, really good. So look at the inserts, look at what they do. And this is just a press with some inserts. So you can make an undercut. So this is a traditional process, but look at what you can do. So you start from a flat sheet of metal and you have a 3D object that is complex. If you think about the case of a computer, they are made like this. And when you have this kind of flexibility, you can even do just one part. You don't need to carry out a batch of 10,000 parts because you have to pay for the molds and dies. Here, the molds and dies are standard, so they can be used for doing many things. And then there is the software part. There are some machines that can handle automatically the sheet of metal under the press, and they tilt the piece and they change automatically the tools. So even if this is a traditional process, automation and software can make it really productive, really competitive. Other examples, this is a ring rolling process, which is really traditional. It is also used for making wheels. For example, the train wheels are made like this. You start from a billet, and then you put it, first of all, in the billet press, you have to create the initial hole. There are nice videos also about forming, because I don't know, you are mechanical engineers, so maybe you can share the same opinion. I like to see the metal working. I don't know what is your feeling, but when the metal is at that temperature, I like it. I like to see it. In fact, I invite you to go to, or maybe we will organize a visit in, for example, in Tenaris d'Armine. I don't know if you have ever been there. You have been there? Awesome. Because it is absolutely fantastic to see their furnace. There are doors that are 15 meters in 8. They open and it seems to see L. It is like L. There is a furnace of 20 meters in diameter, and they melt the metal with sparks that come from electrodes of graphite that are 2 meters long. And you can see the sparks when the doors are closing, and it is incredible. And in fact, you know, in many cases, when there are workers, when you see in a video workers that work really close to a press, managing this hot metal, someone says that it is a bad job. But in reality, if you interview those people, they like it. Obviously, there are some limitations in this. Every worker has to work in the best condition possible, but for sure it is, for a mechanical engineer at least, and maybe not for all of the mechanical engineers, so I'm sorry if I'm stressing this too much, but this is nice. Because you are taking a material that has a very high resistance and you can deform it for obtaining, in this case, a ring. The ring then can be machined, can be a flange, and so on. And again, here there is a comparison And I have another video of forming. I do not switch on the audio, also because my computer told me that I have to reinstall something. And you see in forming, you need high temperature. Obviously here they are starting from a very thick billet. But I would say that all metalworking start from here because in a company like Tenaris Dalmine, for example, they make tubes, but they start from billets. Then when you have the billet, you can roll it, you can reduce the thickness. At a certain point, you can have a piece of metal that can be machined with other processes, but everything starts from here. And in the frame of this course, we will see an application of thin sheets of metal, and this is hydroforming. So under press, you have a mold. So this is the mold. Now the mold closes, and you see that there is water here. In the middle, you can place a sheet of metal, and since on the other side you apply an high pressure, that can be 1000 bars, you are shaping the sheet of metal against the mold. And this is a good advantage because if you see, you have complexity in the mold only on one side, the other side is a cavity. So it is relatively flexible. The drawback of this process is that it is not fast, but it depends. I invite you to consider the time of a process by considering all of the steps of the processes, because maybe thanks to this capability of creating these shapes that are complex, you are saving time in the following processes. So you should never evaluate the performance of just one process in a process chain, because maybe you are compensating. And here, after obtaining that shape, a laser head is creating the holes. It is removing the flash, so the excess of material. And this is a combination of processes. Hydroforming is spread in the industry because, you know, when you have those exhaust pipes for the engines, in many cases they are made by hydroforming. Or even the car cradle, which is the main structure of some cars, is made by a tube that is hydroformed in order to create complex shapes. We will see this process in this course. So forming can be advanced as chip removal processes, as foundry, as I said. So the reasons. Here I make a list just for giving you some ideas about why inventing new processes. And the first one is the topic of the materials. And so the manufacturing and the materials always go together. Sometimes it's a new material that requires a new process. Usually it is like this. Or maybe a process that was not so widespread at a certain point becomes important because it can solve a new issue coming from the materials. So processes and materials must interact. I make an example of ceramic materials. We will see in this course a process called the EDM, electro discharge machining. This process needs that the material is conductive. And so usually ceramic materials are not conductive, but you can dope the ceramic material on purpose with particles with a certain quantity of metal in order to make it conductive enough in order to be machined by EDM. So you see, you can modify the things in order to have an advantage at the end. What is the advantage in that case? is that EDM is really precise. You can make parts at a micron level of accuracy. So it is worth to invest money to create a new material to be machined with that process. You see here a list of so-called difficult to cut materials. Ceramics, because they are hard. Let's try to highlight the characteristics that make this material difficult to machine, difficult to produce, machine is the right term, to manufacture, let's say. Ceramic, as I said, hardness. Composites. What is the issue of composites, like carbon fiber? Composites, by definition, are made by different materials together. So if you have a process, maybe it is good for cutting one of the two materials, but not the other. For example, if you think about the laser, maybe laser could cut the fibers, but then that temperature burns the matrix, the lattice of the material surrounding the fibers. So this is not good. For example, water jet, which is a cold cutting technology that we will see in this course, can cut very easily composite materials. Titanium. Do you know what is the drawback of titanium for machining processes? Maybe you have seen in manufacturing processes 1. I'm not sure. I was sure when I did manufacturing processes 1 because I did that course and then also the following. But I don't know what my colleagues say in manufacturing. They should say titanium is a really nice material. It is very widespread. It is biocompatible. It is light with respect to its resistance, but there is a drawback. The drawback is related to its low conductivity. It doesn't conduct heat. And so this is an issue. When you are machining it, you create heat. And since it is not spreading away the heat, you wear out the tools because the temperature rises a lot. So I cannot push too much on the parameters in milling, for example. I would say that the contrary of titanium under this point of view is what? Can you imagine? So I invite you to think about the properties of the materials. Aluminium. Aluminium is the dual of titanium under this point of view. Even if some characteristics are, let's say, similar. Also aluminium, especially ergal, is strong, light, but it conducts heat and also electricity in a fantastic way. So it is totally the contrary. And there is a drawback also on this point of view, because if I want to cut aluminium by laser, the risk is that the temperature goes away, the heat goes away, and so the temperature remains too low, and I cannot achieve the right temperature for melting. So you see that depending on the situation, you have pros and cons. Aluminium, I have cited it as a metal, but what happens when you have dioxide of aluminium? What is dioxide of aluminium? There is a name. Alumina. Al2O3. And this gives me the opportunity to say that when you create oxides, the oxides have totally different properties with respect to the metal. Because alumina is one of the hardest materials. It can be used as abrasive on grinding wheels. It is used. It is white when you see white. There is another ceramic material that is really hard, and it is the one used for the teeth. Have you ever heard? Zirconia is another material in the family of ceramic materials. And aluminium is really hard. For example, we tried in the past to cut it by water jet. Water jet can be really aggressive, but water jet uses some grains of abrasive, and the abrasive was garnet. That is less hard than alumina. So In reality, you can use a shield of alumina in order to protect, maybe to shield a part that you don't want to touch with water jet, because the jet rebounds and it resists for a very long time. The same for the silicon oxides. They can be really hard, so difficult to machine. Superalloys are Inconel. These are the alloys with which you make the parts of the turbine blades, but also the structural parts of a turbine. The characteristic of that material is that it resists at an high temperature without deforming. Because, you know, if you have an engine of an airplane, you don't want that it deforms based on the temperature. Otherwise, at least the efficiency reduces, but it is risky. So how to machine a material like that is made to resist to temperature? You cannot play on the temperature, or we will see in the advanced manufacturing, the advanced machining part, if you use ceramic tools, ceramic is obviously better because it is a refractory material, can resist at such a high temperature that I can machine superalloy with a very high cutting speed. And it is like we are creating droplets of material in that case. The drawback of this operation is that you can only carry out a roughing operation because it is so stressing for the material that the quality is bad. But if you are doing a roughing operation, you can do it. But in finishing, you have to use the usual carbide materials for machining Inconel. But I make an example of cutting speed. If you use ceramic tools, you can go at 1,000 meters per minute, which is absolutely high. Consider that aluminum can be machined at 2,000–3,000. A good steel can be machined at 400 meters per minute. So you can machine Inconel at 1,000 because you want to go in that region where the material is softened. If you use instead a typical carbide mill, you have to go at 40 meters per minute with respect to 1,000. But you save the part, so the part is finished. I have seen this operation in a company in Emilia-Romagna making turbines for Formula One. I will cite a lot Formula One because I am a fan, but also because their manufacturing plays a big role. I don't know if you have the feeling of that, but those cars exist because manufacturing can do fantastic pieces. Obviously, I am a manufacturer, so I'm saying so, but this is reality. And so I was in that company. They were milling the turbine of a Formula One, and they decided to use carbides, so slowly, because otherwise, since the turbine is made of walls of 1 millimeter in thickness, it would deform, and so it was not possible to manage. Instead, I have also a counterexample. In GKN, which is a company making parts for airplanes, they use ceramic inserts on mills in order to remove a lot of material from titanium parts. Then they finish it. Because the structure of a turbine for an airplane, the stator, is made of parts that are like T, and they machine these T components from blocks of titanium by removing all the rest. When you have to remove such a big amount of material, it makes sense to use ceramics. And then, yeah, cellular structures, metamaterials. So every material has a drawback. So the advanced processes can solve difficult cases. Not all of the cases, but some difficult cases. In other cases, we have another purpose, complex geometries. So what happens if I have to make a very thin wall? For example, we will see that wire EDM can do the job with a very accurate surface finish and a very good quality, geometrical quality. Or maybe in some cases you need the sharp edges. You know, in mechanics, it is difficult to have a perfectly sharp edge because usually you have burrs, flash, so you have to remachine those edges. But there are processes that are better than others. For example, die sinking EDM, that I'm citing processes that we will see in this course, typically doesn't carry out any flash, any burst, so the edge is really sharp. You can do it with milling, but with some strategies. Maybe you have to repass on the same edges in order to remove the burst. You will do it also in the lab. Or undercut. You know, the undercut is a nightmare always when you have to do a part. You know what an undercut is. You have seen in Foundry, for example, where you studied how to remove the core. If you have an undercut, the core is blocked and you cannot remove it. Or in injection molding, making parts of plastic, you have to design the part in order not to have undercuts. Otherwise, the mold becomes complicated because you have to move inserts, like we have seen in forming. You have to remove parts of the mold in order to extract the part. This is an undercut. And making undercuts is difficult. And so you need processes that can enter and work in small areas. I have an example. In turning, you can do undercuts. You can enter with a small tool with a 90-degree insert, and then you can make a radial motion for producing undercut. But not all of the processes can do that. Then for sure, tight tolerances. And this is the case of advanced machining. The first part of the course is about high precision machining, milling. In milling, you can make parts in a range of a couple of microns, so 1,000 of millimeter. So 1 micron is 1,000 of millimeter. We have just installed a machine in our lab. So if you are on LinkedIn, you see the video. It is a Japanese machine. Because we have a research contract with the representative in Italy, and that machine, the first thing you notice of that machine, maybe you will come in the lab and you will see it, is that after the comma in the CNC, it has 5 digits, 5. So consider that the units are millimeters. After the third digit after the comma, this is already micron, but there are also others. So that machine is able to control on the guides the 1 nanometer, which is incredible. Be careful when talking about these small dimensions, because simply the fact that maybe it is not in a controlled environment in terms of temperature, or maybe the sun is shining and it is increasing the temperature in the environment can play a role, and you can have a difference in some microns. The machine is controlled in temperature, so the cutting fluids are controlled and the guides are controlled, so the system is able to stay stable. But the synthesis of this is that when you have to make a part in some microns of tolerance, it is really difficult. Obviously, if you start from a machine like that, the probability of being capable is higher. But some other machines cannot do the job, simply like that. And yeah, residual stresses is also a big issue. You know, when you machine, you are pressing the material or you are stressing under the thermal point of view. And what happens is that that part that you are producing has stresses inside. The problem is that, you know, residual stresses are self-balanced. You should have seen this in some other course. You know what I'm saying. Self-balanced means that if I make a section, I see that the traction stress and the compression stress multiplied by their areas are balanced. So what happens is that if I remove a layer of material, I'm removing also a part of that stress. And so what I will get is a distortion of the part, because the part has to assume a new configuration in order to balance the internal stresses. And this is a very bad situation for every people working in the machining and in the manufacturing field. There is a solution, which is the thermal treatment. If you treat the material in advance, you are releasing the stresses and you don't have this issue. Okay, there is another concept that it comes more on the management side or in the design of manufacturing system. This strange graph is representing what happened in terms of mass production and also what came after the mass production. Because at the beginning, we were here. So craftsmen were able to manufacture just one single part. The variability of the parts was incredibly high. So they made parts on purpose according to the specific need of the customer. But then, as we said, the mass production came into play, which means that the variability and the variety of the parts must be reduced. I made the example of the Model T that was just in one configuration, just one color, because this was the only possibility to produce many things, many cars in that case, and satisfy the market. But then it was not enough, because then obviously when you buy a car, you want some optional, you want a different color. I'm making the example of the car because it is easier, but this happens even in the machine tools or every object, everything. If you think about the mobile phones or the computers, there are different strategies also there, because if I come to Apple doesn't have such a big variety. Okay, in some other cases there is more variety, but you see how industrial things and technical things are intersected with commercial and marketing and everything, and this is normal. In any case, the new processes have been able to create what is called as mass customization. So I have a process and a process chain that is productive, and so I have not a lack of productivity. I can still manufacture millions of parts, but if I manage it correctly, I can change the configuration quickly. This is due to the machine, the software, and the process itself. And this is what we want nowadays, because we are not there anymore, apart from specific cases. And in fact, in the next slide, I will tell you that all of these types of production still exist, but it depends on the product. But for sure, we want a big variety at a low price with a high productivity. These are contradicting things. But who is able to put this together wins in the market. So we have to study processes that are clever, that are more intelligent, more capable of creating complex systems at a low price. It seems in contradiction, but this is the purpose. The components of a mobile phone, even if they are something really incredible, like the sensors, you know, the gyroscope that is inside the mobile phone. I think that the cost of that chip is some euros. I don't know, 2-3 euros. And think about the functionality that it gives. But it is so low because they produce on a slice of silicon, they produce 5,000 pieces together, because it is a batch production which is extremely expensive. But since they are able to produce so many pieces together, the time is short and also the cost is short. It seems a contradiction, but this is doable. But you need new technologies, and you have to be able to manage. For example, if you develop fixtures that are good for many parts, you can easily change the configuration. You can, on the same system, you can manufacture a different part. Yeah, this concept is flexibility. Flexibility in the geometry or flexibility in the amount of parts. And as I was saying, in reality, all of this type of production exists because there are some products that are producing mass production because you don't want a diversity in the products. There are still the artists, the craft, and all of the other things. So we have to be prepared to combine everything existed before with new things. And always when we think about the development of a new product, we cannot think only about a product, but we have to combine the product with the process and the system. The system is the factory, is the process chain made by many machines. The process is every process of the process chain, like milling, like foundry, and so on. And they have to work together in order to make the final result economically competitive. And in fact, it is good if the productive side of a company talks with the design sector of the same company. Otherwise, the risk is creating barriers that do not exist, but at the end of the day, they have a cost. So it is better that everything is developed together. And these are the typical constraints that we have in industry. Sometimes it's just the cost. But if you think about it, the industrial production in the Western countries, Italy makes part of the Western country, we cannot compete here. This is not our ground, our field of play, because we cannot produce parts at a low cost. There are some examples where if you carry out a manufacturing system that is so efficient that you produce many parts, you can also reduce the cost. I have an example of this among the ones that we did in our projects. With water jet, it is possible to cut gaskets. You know what gaskets are, that are sealing components. And in the furnitures, you know, there are those dampers, the dampers of the drawers. Okay. And if you think nowadays in all of the furnitures, we want that because it is nice, because you cannot shut the door, but it is smooth. And in those dampers, instead of the spring, because it is a damper like the one of the car, but instead of the spring, there are gaskets that are made of a foam, closed cell foam, which is elastic. But it is a tube that has a tight tolerance, 0.01 millimeters, or in that range, hundreds of millimeters. And water jet can do this job because it doesn't deform that kind of foam. It is like a sponge. There is a difference between sponge and foam. Have you ever thought about that? A sponge and the foam. The foam is a closed cell foam. It is like the foam that you can have in a bath when you add the soap. Okay, so they are closed cells. If you think about the sponge can absorb the water because it is open. So it is an open structure. So this is the difference. And both of them are difficult to create and difficult to cut. In that case, water jet can do the job. And we help the company for carrying out a plant with 20 cabinets that work together in parallel. And in this way, they increase the productivity. So in this way, you can keep the cost low. But in general, it is difficult in Western countries. Instead, you can be flexible. For example, if you think a third-party manufacturer, you know, the companies that do the parts based on a drawing coming from from a customer, they are able to produce one piece today and tomorrow totally another one because they have a flexible process, and they need to be skilled to do so. And in Italy, we have many companies like that. Time sometimes is a strict constraint. I have another example coming from Formula One, and I talked with the company. The providers of the component of Formula One during the championship. Sometimes they receive the drawing of the part in the morning, and they have to give the part in the afternoon. So they receive the drawing of something they don't know, and in the afternoon, the customer come to take the parts. And the parts are complex and extreme. So you cannot find these everywhere. But in Italy, we are in Italy, so I'm allowed to talk about Italy. I'm sorry for foreigners, but I make a little advertisement. Because otherwise, in the mass communication, I don't know if you hear these news. The news are always bad. I don't know if you have this feeling, but it is strange to hear that we are good in something, but Italy is good in many things. In manufacturing, especially. Obviously, quality. Consider that many of these constraints are conflicting, because I cannot be so fast and at a reduced cost. That company that makes the part in some hours obviously has an incredibly high cost. But it depends on the market where you are playing. So in that market, the customer is available for paying a huge amount of money for having that quality or for having the parts in a short time. In the case of that example, time and quality together, flexibility, probably these are all together, but they are all against the cost. So you have to understand where you are every time. Because the problem sometimes is overshooting, using a manufacturing process that is too precise for something that doesn't work, and so the cost is too much. So for this reason also, traditional processes exist, because not always you need all of these constraints together. In this course, we will see both thermal processes and mechanical processes. And then, as I told you at the beginning, additive manufacturing that inherit some of these characteristics of some of these processes. This is just a list. We will have time to enter into the details, but especially I have just some examples. Let's see if they go smoothly or not. No, this is not a video. In any case, this is a first classification of the processes. You see traditional and non-traditional. I discussed a lot about these terms. We can have multiple classifications, so this is just one. According to this one, you see cutting. If you need to carry out a circular shape, basically you have turning, but then also boring for making precise holes, drilling. If you have a complex shape, milling is the first process to think about, but then there is a list of other processes. I'm not reading everything. Among the traditional processes, there are the ones that are based on abrasive, so typically grinding, when you have a grinding wheel that is used for obtaining a very tight tolerance on a plane, for example. Or sometimes, if you think about owning, it is also useful for obtaining a shiny surface, so like a mirror. Grinding by itself is not done for that purpose. Grinding has the purpose of creating tight tolerance parts. If you want also a shiny surface, you need to apply also owning. And then in the case the abrasives are loose, so they are not attached to a wheel, you have other examples of polishing. Among the non-traditional, there is the list of the mechanical, as I said in the previous lecture, in the previous slide, ultrasonic machining, water jet machining, abrasive water machining. We see in this course all of these processes. Among the thermal ones, electron discharge machining, which makes part of this course, electron beam machining, that doesn't make part of this course. In that case, you use an electron beam, like you know, the cathodic tube that was at the base of all the TV screens. There is a stream of electrons, and with that stream of electrons, you can machine. It is really precise, but really slow. Laser beam machining, ion beam machining. Also, ion beam is not part of this course. And plasma beam machining. Plasma makes part. And here, there are also the last category, chemical, electrochemical, and I never remember the P here. But it is written. You know, under the slides, there is a description. We did a big effort in order to write the comments on the slides because we don't have a reference book. It is difficult to have a reference book because there are some, and I have listed in the syllabus, but they are old, and so it is not the best solution. So I invite you to use the slides and the comments. Then you can also find other information in the books. Regarding the tools, sometimes they can be defined in a deterministic way. If you think about milling and turning, you define the geometry. In some other cases, instead, like in grinding, they are not deterministic because if you think about grinding, you have a wheel made of many grains of abrasive. Every grain is different. So you can just statistically describe that tool. For example, we know that the angles are negative, but we don't have the geometry of every grain in the wheel. And the last category is important for this course because sometimes the processes are based on a tool, which is a beam of energy. Under this point of view, we have laser, plasma, water jet. Even if they belong to different fields of physics, let's say, because water jet is a mechanical process and laser is a thermal one, but there are similarities because both of them are a stream of energy. In one case is thermal, in another case is mechanical. And we will see by studying these processes that also some formulas are similar because of this concept. And yet the videos outside. Let me see. I go ahead and at the end, if we have time or tomorrow, I show you the video. That one was a video about a laser, but I will show you later. With laser, you can do many things. Maybe you don't expect some of these things. Like, for example, you can engrave even glass or marble, or you can cut wood. Probably you have seen something cut by laser. If you go to the fair during Christmas, there are some intricate parts of wood, and you can recognize that they are made by laser because the sides are brown, and that is the signature of the laser. Also, water jet can do something like this, even if it is made of wood, because by playing on the parameters, you are not creating wet parts, because water jet can be so fast that not so much water goes on the wood. And marking is similar to engraving. You go a little bit deeper. This is an additive manufactured part by laser, direct energy deposition. Yeah, if you read the surface modification, because with laser you can also make a treatment, but if you look at this part, it comes from additive. You can weld, you can cut. We will understand in this course that it is not true that you buy a machine, a laser machine, and you do all of these jobs on the same machine, because every application has a different source, different characteristic of the optics, and we will learn in this course how to select on purpose. Let's check this one. Okay.
As erosion continues, the machine controls and advances the electrode through the work. constant gap distance between it and the workpiece.
Now let's do this way. Adesso 1 second. It is a delicate compromise here. Let's do this way. I will show you the videos tomorrow so that I can check it. We were looking at the thermal processes. The video was about EDM, but I will tell you tomorrow. And this is instead the plasma. So in the plasma technology, we have an electrode made of tungsten. Tungsten is a good emitter of electrons. And since you see that there is a polarity, so the tool is negative and the part is positive, the electrons are going to the part. And so there is this possibility for the electrons to eat the molecules of a gas. And the gas is taken there, passing through these spaces. This is the main gas, and this is the secondary gas. If you think about the main gas, it passes to the state of plasma because of those electrons are giving energy and breaking the molecules of the gas itself. And the energy is such that the material here can remain in the state of plasma. Plasma is the fourth aggregation state of the matter. So after the gas, if you break the molecules, you have the plasma. But it exists only if you give energy. Otherwise, the positive ions and the electrons recombine, and so you go back to the state of gas. So in this way, we are creating an electric arc that sustains the plasma. And the temperature here can be even 10,000 degrees, and it is enough, obviously, for melting the material. So we are cutting, thanks to the plasma, not because of the Joule effect of the electricity passing through the part. This is not the main source. The main source, as I said, is the plasma that stays at that temperature that is enough for melting. And then the same gas is used for pushing away the material. So once it is melted, if you design correctly the shape of the nozzle, you are creating a thrust force that is enough for removing the material itself. Also in laser, you have this kind of strategy by using the gas. And these are some applications of plasma. The typical color of plasma is blue, because at that aggregation state, it emits in that frequency. We will come back to the plasma, as I said, also in case of other processes, because the plasma exists also in EDM and in laser in different situations. But as I told you, this lecture is just for giving you some tips. We will have time to enter into the details. This is just a flavor of what we will see in the course. Regarding the mechanical processes, we will see ultrasonic machining and water jet machining. Let's see if I don't create any problem. Yeah, these are just a couple of examples. This is a pure water jet cutting operation on gaskets that are made of plastic material, rubber. And you can do a precise job even on these soft materials. You know, when the materials are soft, they become difficult to cut. If you try with scissors, you know that it is not easy to cut a sponge or a rubber at a high level of quality. And here it is a thin layer of stainless steel. These are springs for an automotive application. And this is a case of high precision water jet. Be careful here because it seems that the cutting head is steel and the material is moving, but this is just because the camera was attached to the cutting head. Usually the part is fixed and the cutting head moves around. Okay, these are the same. And the water jet is very flexible. Remember that the definition of the flexibility in terms of material, because water jet doesn't need that material is conductive, for example. It can cut both brittle materials, even ceramics, or stones, for example. In Italy, there are many applications of cutting by water jet of marble. But it can be used also in industry for cutting precise parts made of metal. And yeah, you find a link here where there is a paper that we wrote for an Italian magazine talking about processes. And this talks about, in particular, microabrasive water jet. That means high precision, because water jet traditionally has been used for cutting in a tolerance of 0.1 millimeters traditionally, but nowadays it is possible to achieve even hundreds of millimeters, which means that the machine is more precise itself and you have more control on the process. So this is just for saying that there are processes that were born precise, like EDM. In EDM, you have sparks, and the sparks remove just a tiny amount of material at a time. So this makes it intrinsically precise. Some other can evolve. And at the end of this presentation, there will be a kind of comparison of performance of processes. And this is what the technologists should know. You should know where you can arrive with the process. And if you cannot do the job with that one, you should have an idea of another one that can machine the same material with a higher level of quality. This is a sketch instead of ultrasonic machine. In ultrasonic machine, we will have a tool that vibrates at typically 20 kilohertz, and it works in resonance. Which is already something strange for a mechanical engineer. So, but we make this on purpose because here there is a stack of piezoelectric material. They create small vibrations of some microns, and we want to amplify it. For this reason, the tool has this shape. This kind of analogy with fluid dynamics. So since the cross section reduces, the amplitude here is amplified. So that here you can have 10 microns or 20 microns of amplitude. And then you use a slurry, so liquid with the grains of abrasive. And this motion will remove material from the workpiece. Ultrasonic machining exists for manufacturing very hard and brittle materials. You can machine ceramic materials with ultrasonic machining. And you combine it with a rotary motion here, and it becomes rotative ultrasonic machining. It is a kind of milling, but it can be done on really hard materials. And this is the traditional. Okay, I will stop in 3 minutes, so we respect the time. I didn't say at the beginning, I start at half an hour, and I do as today without any pause in the middle. Is it good for you? I try to respect strictly this time. In case of advanced manufacturing processes, this is an example we carried out in our laboratory. where we drilled an hole in magnesium. This is a block of magnesium. And here you can see a drill bit. I don't open the video, I will show you tomorrow. But this drill bit had a diameter of 140 microns and the length of 5 millimeters. So 0.14 in terms of diameter and 5 millimeters. So the aspect ratio is really high. We did this for creating a particular device made of magnesium. Magnesium is interesting. It is an interesting material. Under the mechanical point of view, is really bad. So, the performance is absolutely bad. It is fragile. When you machine it, in reality, it is not so fragile. You risk to have built-up edge. You risk to clog the drill bit. But another nice characteristic of magnesium is in the biomedical field. Do you know what it is? First of all, in our body, we have magnesium, so it is biocompatible. And this is really important. The second one is that it dissolves in the human body. So, for example, a nice piece is a stent that is used for children. You know, the stents are the ones that are able to keep a vein open. But the problem on children is that then they grow up. And so if you don't use a biodegradable material, you have to make another surgery in order to remove the old stent and replace another one. Instead, if you use magnesium, you can adjust the duration of the stent so that it dissolves after finishing its job, which is absolutely clever. And so we machined this component for a device, injectable device that has been invented by a spin-off company of Polytechnic. Yes, we are at the end. I show you just this one and then we stop. I will come back even tomorrow. This slide is old, but I project it in any case because this is what we should get from the processes. On the row, you see the processes. And here you see the performance in terms of roughness and tolerance. You have to imagine these colored bars as a Gaussian distribution. These are the tiles of the distribution, and this is the top. So it is something like this. So, which means that the most probable performance of this process, which is surface grinding, is here in the center. Once you have a description like this, you can easily select the processes depending on what you want to get as a final result. So this is the core of the knowledge, or at least a good part, that we need to know for selecting the processes. It evolves during time, so there's no point of projecting the new one, because tomorrow there will be another one. So this is an old one, but the concept is the same. So I invite you to find, if you will use these concepts in the future, in production, to find the performance of the processes. And in this course, we see an overview of their performance. Okay, let's stop here, and tomorrow morning, early, we will be back again. Bye.